talking about capacitors in parallel. Okay, so let's draw capacitors in parallel. So talking about parallel, okay, so there's my parallel plate, there's my parallel system of capacitors. So what we know is that we create a voltage, and that voltage is experienced across this voltage drop from here to here. The change in potential is going to equal my voltage. Now, it doesn't quite work out that easily because we don't have resistors going on. But nevertheless, that these two capacitors are experiencing the total voltage, the change stored here, and the amount of charge that's stored here is equal to the maximum charge that that capacitor is going to store under that voltage, plus the maximum amount of charge that this one's going to store under that voltage. You're not splicing the voltage. You're not forcing charges to behave in a different way. Instead, you have so much pressure at this point that allows to push charge here and allows to push charge here. And that pressure is not being divided amongst them. It's being spread out across the entire system. So I'm not losing that electrostatic pressure. So this total charge, Q, and this total charge, Q, is equal to C times V. C times V. Okay? So the total charge stored in that system is going to equal, Q1 plus Q2. There's the charge here and the charge here is my total charge. Now, doing a simple substitution, I can see that my capacitance total times my voltage total is going to equal the capacitance of 1, or voltage of 1, plus the capacitance of 2, voltage of 2. But the electrostatic pressure, the voltage, is constant. It doesn't change from this capacitor to that capacitor. So that goes away. So you're left with the total capacitance being an additive property. Capacitance total is equal to C1 plus C2. C3 plus C4, C1, whatever. When dealing with capacitors in parallel, now this other one, which is, we found that in resistors too.